Peter Gerard. I work for an organization called Climate Central. I work in communications. I work with scientists. Most of my colleagues are scientists. They're doing primary research and analysis on climate change. And a significant part of the reason we're doing that work, as Mickey reminded you, is to give you a sense of the risks that climate change presents and to make that sense as local as possible so that people can understand it and visualize it. And we do this for a couple of reasons, one of which, of course, is we believe that if you understand the risks, not just as they relate to your security or your safety or your family, but in broader ways, in property ownership, in investment, in sort of larger systems that you participate in, you'll make informed decisions to avoid risk. And the other way, and this is something that Mickey alluded to, the information I'm about to show you, the data, the science that I'm about to visualize for you, it's already well known to all kinds of financial planning organizations, to risk modelers, to the reinsurance industry, to insurers. They're using this information to understand what their risks are, what their costs may be, and they're pricing it, and the pricing is essentially immediately affecting the bottom lines of you and me and everyone around us. And I want you to see it because it affects our everyday lives in all manner of ways. Climate Central exists to make climate science public. We are not an advocacy. I'm not going to tell you policies or politicians to support. We exist to bring science into the public sphere. We work with media professionals. I'm proud to say that I work with media professionals across both sides of the political spectrum, and that my organization is trusted to bring just the science and just the facts in a non-editorialized way so that all audiences can understand the risks that they face and what they can do to essentially keep themselves safe and avoid all of the potential negative impacts, or at least some of the potential negative impacts that a changing climate will deliver to them. I'm going to start locally. So I'm going to start in Fairfield County, and specifically I'm going to start in Fairfield. What you're looking at is a risk map. You can see some red areas on this map, and quite simply, these are areas that are lower than the water level selected here. Right now, that's high tide. We've got a full moon coming tomorrow. So what you're seeing here in these red shaded areas, they're already low-lying lands. You would expect them to be lower than the level of the high tide. They're tidal marshes. And in fact, you would actually see a little more red in this map if we were to update it for the conditions that you're going to see tonight and tomorrow morning. The reason for that is that compared to the early part of the 20th century, there's about a foot more water in Long Island Sound. And that means that when you have an event like a new moon or a full moon, particularly a moon like what we've got this evening or tomorrow evening, a supermoon, it actually pulls more water onto land. So beach parking lots, low-lying roads are going to see water tonight that they probably wouldn't have in those same locations not terribly long ago. My next map I'm going to show is not a sunny day event. I'm going to show you a coastal storm. And this will be a significant coastal storm, one with about a 1 in 10 chance of occurring in 2050. And as you can see, you're looking at flooding that covers significant parts of the area here. This is going deep into residential communities. It's crossing roads. It's getting close to Route 1. 2050 is within the span of a typical 30-year mortgage. And so this is the kind of risk that lenders and insurers are focusing on when they essentially price the cost of insurance. In many of these properties, the insurer is likely to be the federal government. It's likely to be FEMA, which means that the losses are absorbed by us, by taxpayers. And so, this event gives you a sense of what is at risk. And again, you're not looking terribly far into the future. I'm going to look farther into the future now, into the end of the century. And this is that same storm with about a 10% likelihood of occurring in any given year in the 2050s. You're of course seeing a lot more coverage. This means significant damage, not just to homes, but to infrastructure, right? This is covering roads. This is essentially requiring the costs of repairs to be borne, by the town, by the state. One thing I want to note, in fact, two, about this map first is that water behaves really consistently in a model, doesn't behave nearly as well in real life. And so the areas you're looking at, even though you can see them precisely outlined where you can see one side of a road covered and one side not, that shouldn't give you a sense that what you see here is exactly what would happen in a storm. Anything like wind direction and current is likely to change what you're seeing here. It is also not capturing rainfall. So this map is only showing you the height of the water from the open ocean from Long Island Sound. It's not showing you any contribution from falling rain. If you were to look at a storm like this, you would expect rain, which means the risk area would likely be larger. It is also really important to note that as you think about what the risks look like this far out, 75 years out, the spread between the high water and the low water estimates becomes wider. Basically, the chances of significantly more or significantly less water exist because it's so far out, because we can't see the future and we don't know what the pollution profile would look like. We don't know how fast or slow the Earth is likely to warm and oceans are likely to respond. So this is essentially the product of a best guess. It's neither a worst case nor a best case scenario. And we can think about these risks in some very mathematical ways. So what we're looking at here is a time chart showing you something relatively close to this level. So this is 6 feet above the tide line, so here-ish. And in the 2020s, at the early part of this, what you're seeing is this is a very unlikely event. It's got about a 2% chance of happening, which is to say a 98% likelihood that we don't see this kind of a coastal flood in this area. The map I showed you first, that 2050 map, you're still seeing a relatively low risk, but it's triple. You're seeing about a 6% chance of that water level being reached in any given year in the 2050s. Sea level rise is an accelerating phenomena, which means by the time you get to 2100, which is about in the middle of this graph, that likelihood is 98%, which is to say that severe storm is something that in 2100, in this location, based on these assumptions, you would expect to see more or less in any given year. And again, this is the information that the financial industry is using, that insurers are using to understand what the risks are. It's a rare event, but not that rare. This is 12 years ago. This is that same location. This is Pine Creek in Fairfield. This is Hurricane Sandy. So this rare event, it's already happened. We've seen this once. We know what the extent of this damage could be, and we know that we can expect it again. One of the interesting ways to think about what those risks are, apart from things like insurance, is what it could do to local tax bases. So this is a fairly complicated chart, but what it's really telling you is that states determine independently where your property ends and public property or the coastal zone begins. And as waters creep up, one of the things that happens is that private property is lost. Essentially, the rising tide is taking land away, and as it takes land, it potentially takes taxable property with it. So there are about 6,000 properties in coastal Connecticut that would expect to see at least some water from the daily high tide to cover part of their parcels by 2050. And that puts us sort of squarely between Rhode Island and Georgia. If you look to the other side of this graph, Florida has roughly 20 times that exposure. Those are properties expected at least partly to be covered by the high tide 25 years from now. It's important to note that these risks are not necessarily inevitable consequences. There are ways to protect properties, everything from seawalls to elevations and other steps that you can take to try to mitigate those risks. But the risks exist. And of course, the expenses rise. What you're seeing here is, compared to 2020, about 2.5 times the number of tax parcels would be expected to see at least part of their land, part of that property, fall beneath the tide line, potentially off the tax rolls. By 2100, this is out 75 years, 9 times that figure would be improved properties. That would be properties with houses or buildings that are part of businesses put on them. And of course, that ratchets up the expense dramatically. The problem, or at least the complication here, is that as you lose potential tax-paying property on the tax rolls, others have to make up the difference. And the others making up the difference may well be far inland. They may be communities that don't think of themselves as coastal at all. So everything from school buses to other municipal services that might be funded by the property taxes once collected from coastal homes now need to be funded by other sources. And very frequently, those property owners whose properties are very near the coast, they're disproportionately funding the tax base that extends further inland. The loss of that tax base can be really significant. I want to brag about something else that Climate Central does here. So we've been talking about a very local impact. I want to talk about an impact that's not at all local. This is Ho Chi Minh City. This is the Saigon River, and you're looking at exactly that same 10% chance of a coastal flood in 2050 that I had showed you in Fairfield. And as you can see, this is a major manufacturing center, this is an economic center, and this is a disruptive event, the kind of event that can disrupt supply chains. This could affect the movement of goods. This essentially can affect months later what is on supermarket shelves, particularly if this is a broad regional event. So this is a very significant flood, a huge risk that you would expect an area like this to take really meaningful steps, make really large investments to avoid. This is 2100, and again, you're seeing a dramatic increase in what would likely be a disruptive event in a major manufacturing center. And this is where the difference between best case and worst case and the widening spread between those makes a real difference, not just in the defenses that you would have to erect to protect a place like this, but in the time you've got to make the investments, make the plans, and build the defenses that you would need to keep this economy running smoothly and without interruption. And the brag, by the way, is the data that this is based on was produced by Climate Central scientists using original data that was gathered by NASA on the height of the world's coasts. This is more or less the most accurate assessment of coastal land heights available publicly in the world. It has an error rate of around 2 inches, which is to say highly accurate. Climate Central produces this so that countries around the world, communities around the world, can more accurately gauge what their exposure is to rising tide. So I'm going to summarize this part. Speed kills. The time it would take for these realities to manifest can be changed by years, it can be changed by decades, and having an extra decade to prepare for the kinds of risks you see here can make the difference between a community or even an entire nation suffer the kind of disruption that could economically set it back for God knows how long. This is effectively buying time, and the places that can buy this time and the places that can benefit from this kind of risk insulation are the ones that will outcompete others in the future. So this is a critically important piece of information as countries plan their long-term futures and make investments. I'm going to take you uphill. This is a wildfire burning in the Hudson Palisades above New York City. We don't often think of the Northeast as a place that is prone to wildfire, and yet here it is. We've seen this in Connecticut, we've seen this in New Jersey, and one of the factors that is helping this risk manifest is weather, and it's climate-influenced weather. So what people who study wildfires call fire weather is the confluence of warmth, wind, and dryness. And I think anybody who spent any time outside in the last few weeks has experienced exactly that. We are in an extremely dry, unusually warm, and windy pattern that's helping wildfires spread. One of the things I want to point out with the relationship between climate change and wildfire is that climate change isn't necessarily causing wildfire. For the most part, it's humans who ignite fires. It's these conditions that allow them to spread. And if you're looking at Connecticut, you're seeing an increase in those conditions. And this isn't a dramatic increase. You're seeing about 5 extra days in a given year in which wildfires are likely to spread than you would around 50 years ago in the 70s. Not a big increase, but around 25%. If you were to think about what a 25% increase in a variable that affects your insurance rates would be, it's significant. If you look at New Jersey, it's even more significant. That's about a 50% increase over the same time period. You're seeing roughly a month's worth of days a year in which the chances of a wildfire spreading, affecting your property, and effectively ramping up costs, are significantly higher than they once were. Of course, in the East, you don't have nearly the fire exposure that you do in the West. And I don't know if anyone has property or skis, but when you get into high mountain areas and the dry parts of the American West, you've got a wildfire risk that is vastly higher than what anybody here is used to, particularly when you're looking at places like the Sierras in Southern California, the entire Mountain West. You're frequently seeing communities that have 30 and 60 and 90 days in which wildfires are very likely to spread. A lot of people are surprised by West Texas, but there are areas that aren't forested, that aren't at high elevation, that share a lot of these significant risks. And that risk profile is changing. So what I'm showing you here is the change in the number of these days in which wildfires are likely to spread. And you're seeing some of those same areas experience far more days of wildfire risk than they once did, and that is the risk of these fires spreading. Take a look at Maine up in the corner. Not all risk profiles are increasing. You're looking at a place in this map where the number of days where the risk of a wildfire spreading are actually declining. There are a couple of reasons for that. One of them you'll see shortly. In general, the Northeast is getting less dry. We're seeing more rain, we're seeing more humidity, and that affects the profile of fire risk. It affects the number of days that you're likely to see wildfire spread. In Maine, you're also seeing a difference that's related to climate. One of the elements that encourages the spread of wildfire, wind, in that area is partly influenced by the difference between warmer land temperatures and the very, very cold Gulf of Maine. That is one of the fastest warming bodies of water along our coast, which means that the difference in temperature is less than it once was, and that influences the convection behind wind. So you're actually seeing fewer days in which you've got a high risk profile. There's a bit of good news in all of this, right? This isn't a time chart. It's basically showing you the times of year that different kinds of climate impacts, disasters occur. And you're seeing those wildfires at the lower part. You're seeing it as a as a summer and a fall event. I want you to focus on the spring, and you've got that sort of ugly mustard yellow color. That's showing you thunderstorms. It's basically severe storms, and that's what I want to talk about next. When you talk about the risk of thunderstorms, you have a tale of two sides of this country. In the West, as it becomes drier, the conditions that allow thunderstorms to form, and that also means the conditions that allow tornadoes to develop, the kind of damaging straight line winds that you frequently see, massive property damage coming from, the sort of sudden downpours that can trigger flash flooding. These conditions are less common, or at least the conditions that allow them to happen are becoming less common in the American West. This is based on something called CAPE values. If you never remember CAPE values, that's okay. It stands for convective available potential energy, and what it really means is atmospheric instability. It's the energy that allows a thunderstorm to develop. And in the East, you're seeing that energy become more prevalent, and particularly in our part of the East. If you look at the New York metro area, if you look at the Connecticut coast, you're seeing a place where the number of days in which the energy levels are high enough to allow thunderstorm development to happen, increasing by 40 and 50 and 60. So you're seeing an extra month or two where the risk of a thunderstorm developing here become appreciably higher. I want to talk about a couple of the risks that I just mentioned that are associated with thunderstorms. Tornadoes is an area where there is a relatively new body of science about the connection between weather and climate. Tornadoes are famously difficult to study, but you're starting to see some understanding in the scientific community of what changes might be taking place. And here you're seeing a reduction in the amount of energy available to create the storm systems that are typically associated with tornadoes in places like eastern and central Texas and, and in southern Oklahoma. So they're seeing slightly fewer days in which these risks are high if you look at the Mississippi Valley, if you look at the Ohio Valley, and if you look up the eastern coast. The conditions that allow tornado formation are actually becoming measurably higher. So this is something that would be far more rare 50 years ago, far more so now. When we talk about rain, the science is far better known. There is a really simple relationship between a warming environment and the prospects for heavy rain. We know through something called the Clausius-Clapeyron equation that a relatively simple relationship exists between temperature and moisture. For every Fahrenheit degree our atmosphere warms, it can hold about 4% more water vapor. We've had an increase of around 2 degrees Fahrenheit in our atmospheric temperature. That means there is about 8 more percentage points of water aloft. So more rain available to fall. And I should point out, not all precipitation is rain. That also means heavier snowfall is more likely in a warming world. The rub there is that it has to be cold enough to snow. So if you think about places like Watertown and Buffalo that have these like famous lake effect snow events, there is more moisture available to drive even heavier snow. There are also fewer days, even in those places, where it is cold enough for that precipitation to fall as snow. I want to go to some localized information. The closest station I've got for you here is Hartford. And what you're looking at here is an increase in rainfall intensity, and this is very much along the lines of that chart I just showed you. If you remember it not raining as hard as it once did, it's not your memory. This more or less bears out what you're seeing. It is raining harder than it once did by about 10%. And most of the designs that Climate Central puts together are really good. My designers would be completely appalled that I used this one, but I put this together partly to show you that in the same location, you're seeing about 10% more precipitation across the year than you once did. So Hartford now sees in the neighborhood of 4 feet of precipitation a year. That's about a 10% increase since the 1970s. Also associated with thunderstorms, power outages. This is tracking major power outages. These are outages that affect at least 50,000 people or a large amount of power that's sort of equivalent to that. And this is another phenomena and another area of risk that is trending upward. This is reported by the Department of Energy. These are the outages that Connecticut has seen, 68 of them since the year 2000, affecting at least 50,000 people, and they are caused by thunderstorms. Ice storms get about a quarter of it, so it's not insignificant. But between those two factors, you've got about 85% of the causes nationwide of major power outages. And as I mentioned, it's trending upward, particularly as you see this available energy to create thunderstorms. The outcome of that is more situations in which you've got power outages. And of course, power outages are inconvenient. If you have medical equipment that requires electricity, it's more than inconvenient. If you've got prescriptions that need to be refrigerated, or if you simply can't afford to lose what's in your refrigerator, all of a sudden this becomes less than an uncomfortable event. It is an uncomfortable event. These happen in the summer. If you don't have air conditioning, increasingly, you're likely to be exposed not just to uncomfortable conditions, but unsafe conditions. So this is a heat index of 80 degrees, and it's the threshold at which you see higher emergency room visits because of heat illness. It's where you can see heat stroke and even death as the result of exposure to these higher temperatures. You typically think about people who work outside as being the most exposed to this, but of course, if you can't afford air conditioning, this is a risk that everybody faces. And we're back to Hartford, and compared to the 1970s, you're seeing more than 2 extra weeks of temperatures that reach an unhealthy level. That's almost 90 days a year. That's essentially your entire summer. And where you live matters. So this is a map of Hartford, and you're seeing a census tract in the middle of the city. You're seeing an area where there are taller buildings, less airflow. You're seeing paved surfaces. You're seeing building materials that absorb and radiate heat. You're seeing an absence of open land, of trees, of grass, and the result of that is that people who live in the purple area in the middle of this map typically experience temperatures that can be 10 degrees higher than if their environment were built differently. And you can see it in the outlying areas where that impact is considerably less. So again, as the climate gets warmer, as this heat becomes more common, people who live in what's called urban heat islands are more exposed to these dangers. I'm going to show you the mother of all urban heat islands here, which should surprise absolutely no one, New York City. Again, all of those qualities that amplify heat, dense population, tall buildings that block air, not much in the way of parks, open land. It all adds up to experiencing much hotter temperatures, much hotter summers than you would without that environment around you. It means your risk is considerably higher. Those of you who want to take a bit of an eye test, if you can find your way to Manhattan, you can look for something that looks a bit like a sort of keyhole that's a little bit cooler than the area around it. That's Central Park. Still hot because of the environment that it sits in, but measurably cooler than the areas around it. This is a bit of an arcane measurement. We're back to Hartford again, but this is the rising demand for cooling. It's not an economic measurement. It's just the energy required to keep yourself comfortable and safe, and it's about a 20% increase. If you're keeping cool right now, you're using 20% more energy to do that in Hartford than you did a couple of generations ago. And I want to talk about another branch of science that's becoming increasingly important, and that is weather attribution. And weather attribution seeks to answer the question, is this climate change? And the answer sometimes is no. Weather attribution is based largely on modeling. I'm proud to say that Climate Central is one of the leading organizations in attribution science, and we have created models that essentially show the entire world, every place, every day, with and without climate change. We can run those models. We compare the results in individual locations on individual days to see what the temperature would be with and without climate change. And we can use that comparison to tell you essentially how much more likely climate change made a particular day's temperature. We've also worked with an organization called World Weather Attribution. We were actually part of the organization's founding. They're one of the leaders in this science, and somewhat controversially, and we have done the same thing, they have issued statements about major events declaring that climate change did not clearly impact them. In some ways, it's important that people understand the difference and understand that science can tell the difference. So not every hot day is an indication that our climate's changing. I'm going to show you an example of that modeled output and what it means. This is one day this summer, August 2nd, and the interesting thing about this day is not that the heat was extreme, but that it was widespread. So if you're looking at the map on the left, what you're seeing is that most of the country was experiencing an unusually warm day, unusually warm for August 2nd, wherever it was. Temperatures somewhere in the neighborhood of 5 and 10 and sometimes even more higher than they ordinarily would be on this date. It ranges from the Canadian coast all the way down to Mexico, across the Gulf, up the East Coast. And what you're seeing in the chart on the right is how much more likely climate change made those temperatures. In some places, it doesn't make much of a difference. In others, it's at least 5 times more likely, which is to say, if you run both of these models, the temperature that shows up in these areas in the West that are dark brown would be highly unlikely. It is a practical reality that once you get to the point where a temperature is 5 times more likely in a world that's been affected by climate change, you can say certainly that that temperature would not have been reached. This is basically the cutting off point. And that is why the index that you see below, the climate shift index, only goes to 5. After a factor of 5, you already know that these temperatures are the result of our changing climate. Let's go local. So this is the Northeast. This is on that same day. You can see that the temperature departures are significant, but not necessarily extreme on the left. And you can see what impact climate change has made if you look at it on the right. That's elevation in southern West Virginia, where you see that sort of cross. That's an area that without the impact of carbon pollution, without climate change, could not have been this warm. You can say the same for the Chesapeake, for coastal Long Island, for the Cape and Islands. These are areas that are clearly impacted by climate change, where that day's temperature would not likely have been reached. On the other hand, if you look up into Pennsylvania, you're seeing an area where it's statistically influenced by climate change, but not necessarily a clear climate change event. That's about 1.5 times more likely. If you've got good eyes and you can see Erie, Pennsylvania, you can see that white spot. That's an area where, for the most part, the day's temperature was kind of the same with or without the influence of climate change. What we can say about that day is it may well have happened anyway. The temperature may well have been exactly the same no matter what. And of course, here in Connecticut, you're seeing an influence of about 3, which is to say the temperatures here on August 2nd were about 3 times more likely because of climate change. I'm going to take us full circle back to the coast because we can apply those same models to the oceans. September 27th, so a little more than a month ago, and this is the Eastern Atlantic. It is bathwater warm entirely because of the influence of climate change. Instead of going up to 5 where the scale stops on land, we've allowed the scale to show you the magnitude of climate change's influence on these ocean temperatures. It can be in the hundreds. And in fact, in many locations on this map, you're seeing surface temperatures that are made hundreds of times more likely by climate change. Take a look at the Pacific, by the way, where you're seeing areas where you're not necessarily able to detect that same influence. These are areas that more or less are what would be expected, regardless of whether or not we were experiencing a world with climate change with carbon pollution. The reason I picked September 27th is Hurricane Helene. It's forming over some of the warmest water that has ever been recorded in these areas, and of course, hurricanes use warm water to gather strength. It literally spins faster, its winds blow stronger because of the warmth of the water it forms over. And obviously you're watching it here, approaching the U.S. coast. It will become one of the most destructive storms that the U.S. has ever seen. This is absolutely tied to one of the most important and devastating risks of climate change. This storm could not have become nearly as strong without that warm water it passed over. I'm bragging again. In about a week, Climate Central scientists will have the ability and publicly present a paper to connect the wind speeds, the maximum wind speeds of individual hurricanes to the influence of climate change. We'll be able to say how much climate change added to the maximum wind speed of any hurricane. And we'll have analysis that will include this year. So you'll be able to see what the influence on Hurricane Helene was. That's what I've got for you. Framing all of these impacts as part of a risk profile can help you see where climate change is potentially affecting not just you and not just your family, but broader systems, economies, the decisions that will need to be made in the future to keep humans safe, to keep countries profitable. What you need to know personally about your risk is that it's changing. The past is no longer an indicator of what you can expect from weather like this, from impacts like this in the future. It will only get worse. Science is capable of precisely quantifying and becoming even more capable of that, precisely quantifying what those risks look like, what they'll be in the future, and when they will happen. And that means that businesses, industries, companies will all be able to use this information exactly in the same way to quantify what their risks are and to price that. And what happens over the next 25 and 50 and 75 years will change that risk profile. Could change it for the better, could change it for the worse, but for the most part, you're seeing a world in which the decisions we make, the actions we take currently, will change what it costs to live, what risks look like, and how they affect you and your families and your communities for generations to come. That's it. That's all I've got. This is where you can find the information that I've just showed you. All of this is public. It's not behind a paywall. You don't even need to sign up for a service. ClimateCentral.org is that main website. Coastal.climatecentral.org, that's where our maps are. Those are the sea level rise maps that you can explore to see where your community sits and what the risks are. Risk Finder can show you not just the chart I showed you about what the likelihood of a storm is. It will also show you how many people are likely to be affected. It can show you the value of property affected. It can show you everything from roads to hospitals to sites that may be contaminated in the way of coastal flooding. And CSI, that's Climate Shift Index. CSI can show you what the impact of climate change is on any day's weather, any location, any place on Earth. So please feel free to look these up, to talk about them, to understand the risk profile that you're facing, that you may face in the future. Hopefully, it will help you avoid some of it.
Okay, well, thank you so much, Peter, for making the trip to New Canaan. This was a great presentation. And thank you all for coming out tonight.